No? Okay. So, today we're going to learn about torque and how it's related to momentum. Okay, so last time, as you remember, we learned that angular momentum was defined as r cross p, which just means it's the cross product of the radius vector with the momentum vector. Okay? We've learned about the right-hand rule, step along that line. But now let's find out what happens. If you immediately look at this and you say dl dt, well, you say, well, if, for example, if the radius is fixed, then I see that I get dp dt and I get what looks like a torque. But I want to talk about even more generally than that. What happens when we take dl dt? So if I do this, I say this is d dt of r cross p. Then if we remember the derivatives, the derivative of this product then is the derivative of 1 times the 1 plus the derivative of the other. So let's do this out. So I get dr dt crossed with p plus r crossed with dp dt. Now you say to yourselves, well, that's kind of complicated, but there's actually something that's very important and simplifies here. What is momentum? What is the definition of momentum? Mass times velocity. Okay? So if I look at this, and I just bring this out, so what this is really saying that this is equal to dr dt. Sorry, I forgot the vector there. What is dr dt? Velocity. So what I have is velocity crossed with m times velocity plus r crossed with dp dt. But what is the cross product of v with itself? No, there's answer. If I have two vectors in the same direction, so for example, we've often talked about what happens if I have a vector that's one direction, and for example, the radius vector, and then I have a force, a component of the force is tangential to it. That gives me, for example, torque. But if v is in the same direction of v, what's its cross product? Times the sine of the angle between them. And what's the angle between them? 0. What's the sine of 0? 0. So this right here is 0. So even if the radius is changing, what ends up happening is that the torque is still defined as r crossed with dp dt. But what is dp dt? So, sorry, I should have said that this is dl dt. What is dp dt? Force. Right? So what we find out is that dl dt is equal to r crossed with ma. Right? And so if this is ma, but that's the net force, right? Ma is just the net force acting on a particle, and so we see that this is equal to r crossed. So, right? That's how we define the torque. Right? Torque is is equal to r cross force, where this is the net force acting on it. And so we can see that this is just equal to the net torque. So the time rate of change of the momentum is equal to the net torque operating on that system. So I want to do some examples here. We've often taught that if I want to find out the torque on something, I take r cross f. And if I want to find the magnitude, what I say is it's r times f times the sine of the angle between those two vectors. Now that will give you the magnitude, and then you can find direction and stuff along that line. However, you can find direction by simply doing the right-hand rule. But now I want to talk about this in terms of vector form and how we can solve this for vectors. So let's suppose I have a situation where my radius vector is equal to t squared in the I direction plus 3, we'll say 3.0 in the j direction. So what does that look like as a function of time? Here is going to be r of t, sorry, let me put this in x, so let's put this in y. So this is I just want to look at radius vectors as a function of time. So at time 0, what would my radius vector be? I mean, what would at time 0, what is this position vector going to look like? Well, at time 0, this is equal to 0. T squared is equal to 0. And then I have 3.0 in the j direction. So at r of 0, I simply just have 3.0j, right? At 1 second, what do I have? What is this? 1, right? So I get 1 meter in x, and I get 3 in j. So I started here. This is my, what I would call an R0. This is, I have, at 1 second, I have 1 component up here. I have 1 unit in x, and I have 3 units in j. Right? So this would be my, what I can call R of 1 vector. And then at 2 seconds, what do I have? Well, I have 1, 2, 3, 4 in I, and I have 3 in j, and so I'm out here like this. Is this particle accelerating? Is this particle accelerating? How many of you say yes? Yes, right? And we can see that simply because if I look at it as a function of time, this is growing. So, for example, if this said, instead of being t squared, this was just t, then what I would see that along this axis is here, x would just be going at a constant rate. This would just be moving at a constant rate, but it's actually the rate is increasing as a function of time. Okay? And so this is accelerating, which implies that there is a force acting on this particle. So we know that there's a force acting on this particle. That means, since it's relative to an origin, there also is going to be a torque. So let's figure out how we can solve these. I taught you this mathematical tool a little while ago, but I want you to learn this tool because it's a really useful way of studying things, and you're going to need it, especially when you get to linear algebra. It's how you take a determinant of a system. Okay, so what we have here is, so that's my rate, my position vector as a function of time. How would I find my velocity vector as a function of time? Well, I simply take dr dt, right? So if I look at dr dt, this is just a constant, so I don't need to worry about it. It's not changing in time. And so all I have is 2t I hat. Okay? Which means that only in the x direction is there any velocity component that's changing. And in the y direction, there is no velocity. It's just a constant value. There is a velocity in the x, but it is changing as a function of time. Okay? And so this is equal to the velocity, and the acceleration is equal to dv dt, which is just equal to 2 I hat. Okay. So now here's this mathematical tool. And if you can just remember this, this will help you out in when you get to linear algebra. You haven't already had that. So I'm going to show you how to take a determinant. If I have two vectors, and I want to find, for example, r cross v. How do I find r cross v? Well, this is a nice way of doing this in vector form. Instead of worrying about this, so if I look, for example, in our normal technique, dr dt, what is the velocity at time 0 for this particle? The velocity at time 0 is 0, right? Because I have 2t, so the velocity at time 0 is 0. So it's just, there's no movement in y, but what you can think about is this particle starts from rest at time 0, and then just starts accelerating along here at a distance of 3 meters away from the origin. Okay? So what I could say is at time 0, r cross v is 0, because r, I put my fingers in the direction of r, and then I wrap them in the direction of v, but there is no v. Right? At time t equals 1 second, I put my fingers in the direction of r, but now I see that v is moving along this direction, so I have r cross v, and so the r cross v is going to be into the board, right? So that means the angular momentum is going to be in the board. Now let's look at dl dt, or the torque. But first, let's do r cross v. So here's how I'm going to find this. What I do is I say I have 3 components in 3 dimensions. I have an I hat, I have a j hat, and I have a k hat. So my first row here, I'm going to make a 3 by 3 matrix. And what I'm going to do is my first row I'm going to do is say I, j, k. My second row, I'm going to put my radius vector in. So what I have in my radius vector is t squared I, so that goes to my first one. So I just write t squared here. The second term is a 3j, so I have 3 under the j, and then in k, what do I have? 0. Then in the third row, I do my v. Okay, so then I go to my v, and I can see that that's simply just 2t. I don't have any y, and I don't have any z. Okay, so what we do at this point is then we write out, we take this first term, we write it I. And then when I have I get rid of that row, and I get rid of this column, and then I simply just look at what's happening here, and then I go this term times this term minus this term times this term. So I get 3 times 0 minus 0 times 0. Now that's fairly obvious that that's 0. Okay, so I take the first term, and I take the first term, and then I multiply this minus these 2. Then I take the next term, but now, to be careful, I do a minus j hat. So the first term I just do plus, the second I do a minus, and then I get rid of this row, I get rid of this column, and then I get t squared times 0 minus 2t times 0, which is once again 0. Then I do a plus k hat. then I get rid of this row, I get rid of this column, and then I just do t squared minus 0 minus 2t times 3. So this is the only term that's non-zero. So I get a minus 2t times 3. So I get 6t, and it's a negative. Okay? So the result is that this gives me a minus 6t k hat. So that is my angular momentum. Now, is this what we would expect? Well, let's think about the direction. Which direction in an XYZ system, in a right-handed XYZ coordinate system, I have X along here, I have Z, Y along here, and then I have Z coming out of the board. So what we would expect then is that this is going to be negative and the negative Z, along the negative Z axis, right? Because if I take R cross with V, it gives me into the board, and that's what we see here. But now, the nice thing about using it in this way is that we actually know what the magnitude is as a function of time, and we know its direction. So this is a really useful way of keeping track of things. So let me just go over that technique one more time in doing R cross A, or finding the torque now. Oh, we're going to get rid of that. Where did I put my check? Oh well. Okay, so this is how we found R cross V. Now, what about R cross A? Well, R cross A is also important because if we know R cross A, then we can find the torque. So if I do this again, I say I, J, K. What am I going to put here? What's going to be the first term here? It's going to be t squared. What's going to be here? 3. What's going to be here? 0. What's going to be here? 2. What's going to be here? 0, 0. So let's do this out again. So this is going to be equal to I, we get rid of the column, we get rid of the row, we only look at what happens, and I take this times this, minus this times this. And so I see that's just 0. Then I'm going to get minus, I do the minus, j hat. I get rid of this column, get rid of this row, and I get t squared minus 0, 2 times 0, and that gives me 0 again. And then I get plus k. Then I'm going to get, I get rid of this column, get rid of this row, and I get t squared times 0 minus 2 times 3, and so I get minus 6. And so we see that this is equal to minus 6 k hat. So that's the torque. It's a constant torque operating on this system. Or I should say there is a constant torque on this system. Due to the fact that there is an external force acting on this particle causing it to accelerate. Okay, this is an extremely valuable vector technique for finding cross products. And I hope you all feel comfortable in being able to do this, because it's a lot easier to think about doing this than writing down the equation that they just showed in the book. Yes?
Could you work down a general case using variables instead of numbers? Because I'm a bit confused as like what came from where.
Variables instead of numbers?
I'm confused like where you're getting your numbers from.
Where I'm getting t squared and 3.
So like, and when you translate that to these linear equations for like everything that's constant, it seems kind of arbitrary.
So you're wondering about where these came from?
Yes.
Okay. So what we can say is that, yes, that's a good point. So suppose I just have A. A is equal to AX I hat plus AY J hat plus AZ K hat. hat, and V is equal to Bx I hat plus By j hat plus Bz k hat. That sound okay? And then if I put that out, then what I say is I, j, k, and then I have an Ax, Ay, Az, Bx, By, Bz. What I do is I hat, Ay times Bz minus By Az. So I just do, I want to look at this times this minus this times this. Then I take a minus j hat, and then I look at Ax times Bz minus Bxaz. And then I do a plus k hat, which is Ax By minus Bx Ay. Does that make sense? And so you can do one of two things, right? You can just say, oh, this is the formula that we use when we do cross products, or you can just remember this technique. And I prefer that you remember this technique because that will be more valuable in the long run than just going and memorizing and writing this down. Yes?
Is the form always going to be I minus j plus k?
Yes. And in fact, if you generalize it to higher dimensions, what you end up doing is just plus I minus j plus k minus with here plus minus plus minus plus. And then what you have to do is find the determinant of larger dimensional systems. But this is for three-dimensional system that works. Great. Okay, good questions? Any other question? All right. So if you can do this, it'll make your life a lot easier rather than just going back and referencing this every time and sticking in all of the various terms. Okay, now, any other questions? So, what if I have multiple particles? So, suppose I have multiple particles, then what I'm going to say is that L is simply, I'm just going to call this a total angular momentum of the system. This is going to be L1 plus L2 plus L3. It's just the vector sum of all those individual angular momenta. So that gives me the total angular momentum of the system. Okay? Now, if I look at dl dt, what do I get? Well, if I take dl dt, I want to find the time rate of change of angular momentum of the entire system. Then I simply just take dl dt of all of those individual angular momenta, right? So if I have the angular momentum of particle 1, I take its time rate of change, I add that to L2, L3, Ln, so on and so forth. I end up getting this. But this just ends up being the net torque on particle 1, the net torque on particle 2, the net torque on particle 3, so on and so forth, right? And if I simply add those all up, what I end up getting is the net torque on entire system. So there's an important point to keep in mind here. Particles within the system can exert a net torque on each other, right? Particle 1, so let's say I have an isolated system, and this isolated system, there are lots of particles in this isolated system, and let's suppose that these individual particles are exerting torques on each other. Well, that's true, but for every torque that particle 1 exerts on particle 2 is exerting an equal and opposite torque on particle 1, which means that essentially all the internal torques, their sums add to 0. So what ends up being important is the net external torque on the system. Okay, so last time we talked a little bit about, for example, a motorbike in the air. And if you're a motorbike, if you put on your brakes or you let go of the accelerator, so you go off of this jump, right? You hit the brake, you're causing a torque on that tire. But the whole system is the motorbike tire system, right? You're exerting an internal torque on that tire, right? Which means that what really ends up being important is the net external torque, and we'll talk about this a little bit more here in a minute. But what ends up being important in terms of the change of angular momentum of that entire system is the net torque being operated on that system, external torques. Okay, so for example, a wind shear or something along that line, if that motorbike is in the air, that would cause a torque on the system. But the other internal torques won't change the total angular momentum of that system. Okay, so now let's think of a rigid body. What do we know about a rigid body system? We know that, if you look at this, it makes sense. There's kind of an intuitive sense. But a rigid body is a simpler case of all of this, right? Because when we have a rigid body, everything's rotating together. And it's a simpler thing than considering the individual dynamics of every particle. Now what we're considering is everything moves uniformly or moves together. For example, like this bicycle on our system here. This is rotating. This is rotating everything together as a constant angular velocity. Everything's moving, rotating around at a constant angular velocity. So we have a similar thing here when we consider a generalized rigid body. Right? So for example, suppose I have an object, and here's my origin. I'm going to try and draw this in 3 dimensions. And I have something that's out here, and what I'm going to do is I'm going to rotate it about some axis. Now, because I can rotate it about any axis, I can just move my coordinate system until the axis aligns with the z-axis, right? Just for simplicity. So I can... Okay, very good. So this whole thing, I'm just going to say, so let's do the bike again, right? I can have this rotating about this axis right here. Now this is kind of at an awkward angle, but I can just simply move my coordinate system so that I define this to be the z-axis. That's all I'm saying. So it doesn't, we're not losing anything by just choosing it to be rotating around the z-axis. Now, if I look at an individual particle here, so I have some radius vector going up to a little tiny piece of mass that we call delta m. Right? I have a delta m here, I have a little delta m over here, I have a delta m over here, and all I'm doing is I'm adding all of these little tiny masses together. So, how would I find the angular momentum of this rigid body. How do I go about doing that? Well, I can find, first of all, I can find the angular momentum of one of the individual little tiny mass elements that I'm talking to here. I can just call that delta M1. Okay, so we can do that. So basically what she was saying is I can just call this little mass element, and then I can sum over all this or integrate, and that will give me the total angular momentum of the system, right? I can do this. I can find the little angular momentum for this mass 1. I can find the angular momentum for this mass 2. I can find the angular momentum or the torque for mass 3, so on and so forth. But let's look at the total angular momentum. So what I have is, so let's just do, so we're going to do the first one, which is a little tiny mass element, which I'll call delta M. Okay, so all that means is I'm just going to say, here's a little tiny mass element, delta M, and I'm going to call it delta M1. So we know that that's a mass. And how about its radius vector? Well, I can just call that R1, and I cross that with V1. Okay? So that gives me the angular momentum of that particular mass element. Now, how about this particular mass element? Well, I simply do the same thing again. I have delta M1 R2 crossed with V2. Oops, sorry, I didn't do delta. Plus delta M3 R3 crossed with V3, right? Okay, so this has simply allowed me to sum up the total angular momentum of this entire system. Now this is a little bit complicated because this is still kind of treating all of these particles as if they were independent free particles. But there's something very important about a rigid body, right? All of these are rotating about a single axis. Right? We said that all of these are rotating about this axis. So we can imagine we just have this. So let me do this with this bicycle is turning out to be extremely useful. Bicycle wheel. What I can say is for example, here's my origin right here, and I just spin this around. Here's my origin, and if I want to look at my angular momentum at any point, I just go up with my radius vector coming up to this point, or a radius vector coming up to here, and I find the mass at that particular point. I do R cross V, the velocity of that point at any one individual time, and I can find the total angular momentum. But the beautiful thing is, this all has the same angular velocity, and it's all moving, and the angular momentum of all these individual particles is in the same direction, right? So these are all pointing, so there's a nice easy way of thinking about angular momentum, is if I have an object that's spinning around, all I need to do is wrap my fingers in the direction that it's moving, and that's the direction of the angular momentum. Which direction is the angular momentum for particle 1? Right, so if I have a particle, I come up here, and let's say this is all spinning around right here, right? So for example, suppose my radius vector is coming out from the origin, and I go to my velocity vector. Which direction is my angular momentum going to be pointing? So R cross V is up like this, right? Now, if I go to another point on this tire, R cross V is up. If I go to another point on this tire, R cross V is up. In other words, they're all adding in the same direction. Right? So I go R cross V is up, R cross V is up. They're all pointing, if this is spinning around, I go from this point out to on this distance over here, on the tire, then what I see is that they're all pointing in the same direction. That means R cross V is in the same direction. So we can simply add these as individual components in the Z direction. Okay? Okay, so what I'm going to do is I'm simply going to say that this then becomes, what I'm interested in is, let's consider L, magnitude. We know that we can add them now all the same, so we say this is delta M, and then I'm going to have R1, and then this is going to be V1 sine of the angle between them. Okay? Plus delta M2, R2, V2 sine of the angle between them, so on and so forth. Okay? Now, this, if I think about what R1 sine phi 1 is, what is that? If I think about a vector here, if I think about a vector that's coming out, I'm going to call this R, and I call this angle phi. Sorry? Okay, it's the component that ends up being vertical, that ends up being perpendicular to the velocity. Okay? If you want to think about, because what I have here is, suppose I'm doing this about the z-axis. Suppose I have a radius vector, right? And I'm coming out here, and the velocity is, for example, going around like this. Okay? And I simply am going to take the component of the radius vector that is perpendicular to this rotation of motion. So this allows us to do something that's very nice, which is that we end up saying this is delta M, R1 perp, V1, plus delta M2, R2 perp, so on and so forth. But V1 is simply, if I take V1, this simply ends up giving me omega times R perp. Let me write this out. Okay, so what we end up getting is a sum. I have a mass element times a radius squared. I have a mass element times a radius squared. But what are these? If I sum up all of these, that simply gives me a moment of inertia. So So what I end up finding out is that the total angular momentum is simply I omega for these rigid bodies. Okay, now, if I have an isolated system in which there are no external torques, let's see if I have an example. Okay, yeah, so let's so conservation conservation of angular momentum. If I have no external torques acting on the system, then the LDT is equal to what? If I have no external torques, what's dLdt? 0, right? Which means, if there are no external torques, dLdt is 0, which means that if I have a system and I go from one time to another time, what I find out is that L final, the angular momentum, final is equal to the angular momentum initial. Now this is kind of neat, because what this says is, what if I am, what if my initial, what if something changes while I'm doing this? For example, remember how I had the weights, when we did the weights spinning around on the chair, right? There were no external torques. But as I bring in those weights, what happens? The moment of inertia gets smaller, right? So what has to happen? The angular frequency has to go up. That's right. So that implies that I1 omega 1, or I1, let me put I final omega final, is equal to I initial omega initial. So if the angular momentum is constant, that means that for a rigid body, or this particular system, that I final omega final is equal to I initial omega initial. So if this goes down, if the initial moment of inertia goes down so that the final moment of inertia is much, much smaller, that means that the angular frequency has to go up. Okay, so let's do an example of this. A little while back I said that you can have a lot of fun on a merry-go-round. Let's do a quick check of what that might be like. Okay, so here's the scenario. Suppose I have a merry-go-round. Let's just say this radius is, say, 2 meters. It's a relatively large merry-go-round. Let's say there are 5 people on the merry-go-round. And let's say 4 of them weigh 100 kilograms. And we'll say one of them weighs 50 kilograms. Okay? So what we're going to do is at some initial time, these 4 heavier individuals are going to be, they're all going to be at the 2 meter radius. And then what they'll do is the 4 will come in while leaving their 50 kilogram friend on the outside, and we'll see what that person experiences. Okay, so what is the moment? So I'm going to assume that this whole disk is 200 kilograms. Okay, so, and we'll assume that it's actually a uniform disk. just for good reasons, okay? So what is my initial moment of inertia? Well, I'm going to have M, so I'm going to have the moment of inertia of the disk. Then I'm going to have 4 times the moment of inertia of the friends, or maybe I should say heavy friends, plus the moment of inertia of the light friend. Right? What is the moment of inertia of a disk? mr squared over 2. Okay, and I'll just say the mass of the disk plus the 4 times mass of the heavy friends times the radius squared plus the mass of the light friend radius squared. Okay, so let's just solve this out. So we have M, this is 200 kilograms divided by 2, so we get 100 kilograms times r squared. We get 100 kilograms here, 400 kilograms here times r squared, plus 50 kilograms. So we get 100 plus 400, so we get 550 kilograms times 2 meters squared. Okay, so we see that this just gives us 550 times 4, so that's 2,200 kilogram meters squared. Okay, now how fast do you think you can get a merry-go-round spinning? I mean, just think about it. Fastest you've ever gotten one going around. How long does it take one to do a complete circle? And you're just sitting there as fast as you can. How long did it take you to get to make a complete revolution? I don't know. 3 seconds? 2 seconds? 3 seconds seem reasonable? Yeah, let's use 3 seconds. Okay, so 1 revolution takes 3 seconds. Okay, so if 1 revolution takes 3 seconds, how many pi per second do we have? Well, it takes 2 pi to do 1 complete revolution. And so what we're interested in is what is the angular frequency, right? Omega I is equal to 2 pi times the frequency, right? And the frequency is just 2 pi times 1 over the period. And we said the period was 3 seconds. And so we see that this is 2 pi over 3. All right. Now, that's the initial. Our second thing is, now we're going to have all of these friends go to the center. Okay, so we're going to have these 4 heavy friends go to the center. So what is mr squared going to be for these guys? 0. It's not 0, but we're just going to assume it's 0 because these guys have some finite width, right? So now I final is equal to the I times the disk, that stays the same, plus only the mass of the light, only the moment of inertia of the light friend. Right? So in the end, this gives us 100 times 100 kilograms times r squared plus 50 kilogram r squared. And so we see this is 150 kilograms times r squared, which we said was 2 squared, so we get 4 times this, 4 meters squared, so we get this is 600 kilograms meters squared. Okay, so I the moment of inertia initial times the radial velocity initial is equal to the moment of inertia final times the angular frequency final. So omega final is equal to the moment of inertia initial divided by the moment of inertia final times omega I initially. So this is I initial is 2200 and I final is 600. And so let's just approximate this as being 4. So I get 4 times 2 pi over 3. Right? And so we see that this gives us 8 pi over 3. And we should write it clear, this is in per second, right? So this is radians per second. So how much force does that 50 kilogram person have to exert in order to stay on? Right? Because that 50 kilogram person has to stay on. So what we did, is we just have, there are those bars that come around this side. We just have people with the bars coming right here onto their shoulders, so that it was a very, very intense experience. But it's pretty fun. So this means omega. So how are we going to find the acceleration? Well, acceleration, let's just do this in terms of g's, right? Is v squared over the radius, right? But what is v squared here? What is v in terms of r? Okay, so we get omega times r squared all over r. And so we see that this is omega omega squared times r. Right, so let's do this out. We have 8 pi over 3 squared times the radius of 2 meters. And what does that give us? So this gives us 64 pi squared all over 9 times 2. And so 64, what pi squared is approximately 10. So we get 64 times 10. So we get 640 divided, let's just say this is approximately 10 because we're just doing everything, we're just doing approximates. So we'll divide by 9, just say it's approximately 7. So it's about 140 meters per second squared. And what is g? What is g? Approximately 10, right? So 14 g's. Now, this doesn't actually happen. You can't get it this fast. And what do you suppose? Why can't you? I mean, it's pretty intense, but it's not like this. Where do you suppose we can't make it? The heavy friends, you just can't get to the center. The forces become so great as you're trying to get to the center that it's Herculean if you can make it. It's really you're pulling with all you've got to get to the center, and it's just too much. But anyway, it's a really interesting experiment in forces if you ever want to try it. So. So this is a classic example. Now, once every 3 seconds isn't perhaps that fast. You don't think about going around one time every 3 seconds as being that serious. But by the time this happens, right, you're going around more than one time per second. 8 pi over 3 exceeds once per second. So this ends up being a very, very high high force for those who are trying to hold on to onto the edge. So that's just an example of conservation of angular momentum. So now I want to do another example. Can I have an audience member? Someone, you don't have to be brave physically, just brave emotionally, socially. Who wants to be socially brave? We've all seen that. Are you taking off your scarf to be socially brave? Okay. I just need someone. What we're going to do is we're going to spin this tire around. I need you to hold the tire. We're going to spin it at a pretty high speed, and then what we're going to do is simply switch directions and see what happens. Anybody want to do this? You all heard that song, right? Let me see how big your brave is. No. Oh, I guess I'll have to do it myself. No takers? Okay, all right. Good job. So, what we're going to do is we're going to get this spinning around. Okay, maybe you have to be a little brave. But can you hold it like that? Okay, now sit down. Okay, now switch. No. Okay, now switch the other direction. Okay, now switch back. Pretty cool, huh? Okay, you can just do another grab. Well, it doesn't shoot out of your hand. Okay, so what's happening there? Thank you. Okay, give a big round of applause. Well done. Pretty hard to turn it, isn't it?
Yeah, that was definitely not what I was expecting at all.
Okay, so what happened? What was happening? Why when he switched directions, did he start moving the opposite direction? Okay, conservation of angular momentum, right? What we have is, if this is spinning around like this, angular momentum is like this. Now I switch it down, which direction is angular momentum? But we have a closed system, right? So what had to happen? He had to compensate, right? He had to start spinning in the opposite direction to get the angular momentum to be conserved, right? So his the initial angular momentum was all this spinning, and he had no angular momentum. But then, as he flipped it around, right? As he flipped it around, then the angular momentum was pointing the opposite direction, which means in order to conserve that, he had to give an angular momentum in the opposite direction of the change. Okay? So, just a fun little thing to do. All right, so let's do gyroscopes. You've all seen tops. You've all seen tops that when you start spinning them, they start to precess around. So what is driving that? And we're going to see this in just a second. We're going to do a very similar thing here. What we're going to do is get this spinning around, and then we're going to show, if I don't kill myself, that this, or at least badly named, that this will actually precess. Okay, so we know that tau is equal to dl dt. Okay, so now suppose I have a situation, and it's going to be just easier for me to show this rather than to try and draw it because I don't draw well in 3 dimensions. Okay, so if this is being held, right, I'm going to hold this like this. It's being held right here. This is the axis, it's going to rotate about this axis. My lever arm is going from here, about the axis of rotation, to the center of the mass of this bicycle wheel. Okay, so that's going to be my radius. Okay, and what is the torque that's going to be operating? I mean, what is the force that's going to be operating on this wheel? So I'm going to hold this in here like this. It's going to be supported, but if I look at the center of mass, what's operating on the center of mass here? Gravity, right? And gravity is going to try and do what? Gravity is going to act on the center of mass going this way. And so which direction is the torque going to be? I take my radius vector, I cross it into my force, and my torque is going to be this way. Now my change in my angular momentum, now because, and this is a very important thing to understand, is this is spinning around at a high speed, right? Is that torque going to cause the speed of this tire to change? Does gravity acting down this way cause the speed of this tire to change? What do you think? No. It's going to keep on spinning in the same amount. So we know that torque is the time rate of change of the angular momentum. But it isn't that it's making the angular momentum decrease by making the spin go slower. What's happening? Has to change direction, right? So dLdt can be more than just a magnitude change. It can also be a direction change. And so this is a classic change in forces, a change in a vector where the direction is changing, but not the magnitude of this. So let's look at this carefully. So let me just put here gyroscope. Okay, so this is, we're just going to look at a gyroscope. And now what I'm going to say is this is dl is equal to tau dt. Okay, so the change in the angular momentum is equal to tau dt. You'll see why in a second why we want to do this. But how do we define the magnitude of the torque? How do we define the torque acting on this? R crossed into the gravitational force, right? So it's mg. It's the mass of the object times g times the radius, right? mgr. Mg is the force. The radius r times the sine of the angle between them. What's the sine of the angle between them? As I'm holding it like this, it's 90 degrees. So the sine of 90 is 1. Right? So we get mgr. Let me just do this as magnitudes right now because we'd have to say what the direction of that is. And we just want to write it like this. Okay, so we're interested in the magnitude, which is just, we just write this as dl is equal to tau dt, which is mgr dt. Now, so if I'm holding this out like this, I have the radius, I have the force, mg, the torque is going to be in this direction. That means that is going to be the direction that the torque is applied to it, which means that's the direction in which the angular momentum is going to be changing. So if I look at this on a big circle, now I'm looking at that from a top, I'm looking from a top view, right? And suppose I have the bicycle wheel is spinning right here, and now this bicycle wheel is going to precess around here like this. And I look at my radius vector. My radius vector is just centered around the string. So you can imagine I have the string centered up here, and that this is going to precess around like this. Here's my radius vector. Then I'm going to have my force going into the board. Right? this is going to start going around like this. Okay, so what I'm interested in is how little dl is related to big L. Okay, so if we think about this, now this is a little bit abstract, but because now what we're interested in is rate of change of L, magnitude of L, and dl. Okay, so suppose I have some L here, and my dl is, so we know that if I look at L here, which direction is L for this bike, spinning bicycle tire that's spinning around? Let's suppose it's spinning around like this, right? Then L is this way. But which direction is dl, the change in the momentum? It's this direction, right? In the direction of the torque, because the torque is causing it to have a change in angular momentum that's going this direction. So L is in this direction, dl is perpendicular to it, or the change in the momentum is due to the change in the direction of the momentum. And so what we can say is that dl is related like this, and this angle, which we call d phi, is related here by saying that d phi, or that change in direction, is equal to the small unit over L. Right? For small angles, we just used that d phi is equal to dl over L. Okay, so that means we can then use this equation right here, and we have that this is mgr all over I omega, because L is equal to I omega. And then we're going to have that this is multiplied by dt. So if we divide by dt, we get that this is d phi dt is equal to mgr over I omega. So this gives us, but what is d phi dt? That's the time rate of change of an angle, right? And what is the time rate of change of an angle? It's an angular frequency, or how fast something is rotating. Now, it's not this omega, right? That's how fast the tire is spinning. This omega that we get here, we'll write as a capital omega. This capital omega is how fast it's going to precess about that origin. Okay, so let's do, have any brave audience members after seeing the first extraordinarily brave act of physics? Anyone else want to do it? Are you raising your hand? No? Okay. You are? You want to come do it? No? Oh. Sure? All right. Okay, I'll do it. Okay. Now I want you to notice, as this slows down, what happens. As the speed of the tire slows down, have you noticed anything about the precession rate? It's speeding up. Right? Look at how the precession rate is related to the speed of the wheel here. Probably should have stopped that. Okay. Would anyone like to okay, so what we'll do is I'll end this a little bit early, and anybody that wants to come and try this without the fear of doing it in front of their peers, come down. But let me just say, this is fun stuff. We could have determined the speed that was going simply by knowing all of these other parameters and seeing what the precession rate is here. Does anyone want to come try this?